Radioactive Decay Law. In this fourth nuclear physics video, we will discuss radioactive decay law. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. We saw in the last video that radioactive decay is a spontaneous process, which means that we cannot predict for a particular nucleus when it will happen. This is a random, spontaneous process. So we can see that the decay process is probabilistic and can be described with statistical calculations for a radioactive substance of macroscopic size containing a large number of radioactive nuclei. Thus, the probability that an individual nucleus will decay is the ratio of the rate of disintegration to the number of radioactive atoms present at that instant. We can mathematically quantify the probability as follows. The probability lambda is called the decay constant and is different for different isotopes. We can multiply both sides by n to obtain the rate of disintegration. As time passes, the number of radioactive parent atoms present will decrease. So, in order for the formula to reflect this, it needs a minus sign. If we take the limit as delta t approaches 0, we obtain the instantaneous rate of disintegration. This last equation can be solved for n using calculus, and the result is. This equation is called the radioactive decay law, where n is the number of radioactive nuclei present at time t. N sub 0 is the number of radioactive nuclei present at time t equals 0, and E is Euler's constant. The figure below shows the decay graphs for 3 different isotopes, each with a different rate of decay. Isotopes with a large decay constant decay rapidly. Those with a small decay constant decay slowly. Another useful parameter for characterizing radioactive decay is the half-life. Half-life is a way of measuring how long a particular type of radionuclide lasts. Now let's see what is the relationship between the decay constant and the half-life. The half-life of any radioactive element is defined as the time it takes for a number n of parent radioactive atoms to decrease to half of the initial number. To find an expression for the half-life, we start from the radioactive decay law and we replace n with n sub 0 divided by 2 and t by the half-life. By cancelling the n sub 0 factors and then taking the reciprocal of both sides, we obtain. Taking the natural logarithm of both sides gives the expression that connects the decay constant and the half-life. The figure illustrates the exponential nature of the decay and shows the fraction of unstable isotope left compared to the half-life. Let's solve one example to make the theory clearer. To solve item A, we use the definition of the mole and Avogadro's number to find the number of nuclei that we have initially in the sample. The atomic mass is 13, so 13 grams will contain a number of nuclei that is equal to Avogadro's number. So the number of nuclei that we have initially is given by the ratio. To solve item B, first we use the expression that connects the decay constant and the half-life to obtain the decay constant. We now use the radioactive decay law. Physicists are generally more interested in the decay rate than the number of radioactive nuclei itself, because the decay rate of a sample is a more direct, experimentally measurable quantity. The decay rate or activity of a sample is defined as the number of decays per second. The decay rate can be obtained by combining the equations above. The SI unit for activity is the becquerel. 1 becquerel is simply equal to 1 disintegration or decay per second. A frequently used unit of activity is the Curie, and it is related to the SI unit as follows. Let's solve another example. To solve item A, we use the definition of the mole and Avogadro's number to find the number of nuclei that we have initially in the sample, as in the previous example. To solve item B, first, we find the constant decay, and then we multiply the number of nuclei that we have initially in the sample by the decay constant. To find the activity after 4 hours, we take the formula above and perform the calculations. One of the most interesting applications of the law of radioactive decay is carbon-14 dating. Carbon-14 dating is a technique used by scientists to date bonds, wood, paper, and cloth. Let's see how it works. Carbon-14 is an isotope of carbon. It is produced in the Earth's upper atmosphere when nitrogen-14 is broken down to form the unstable carbon-14 by the action of cosmic rays. Consequently, carbon-14 formation occurs at a constant rate. The unstable carbon-14 is transported down to the lower atmosphere by atmospheric activity, such as storms. Since all life on Earth is made of organic molecules that contain carbon atoms derived from the atmosphere, all living things have about the same ratio of carbon-14 atoms to other carbon atoms in their tissues. Once an organism dies, it stops taking in carbon in any form. The unstable carbon-14 within the organism begins to decay to form nitrogen-14 by emitting a beta particle. Over time, the amount of carbon-14 in the material decreases, and the ratio of carbon-14 to other carbon atoms declines. By measuring the amount of carbon-14 in a sample and comparing it to a fresh sample, scientists can determine its age. The fewer carbon-14 atoms in a sample, the older that sample is. Let us now solve 2 examples to illustrate the dating of biological tissues using carbon-14. We took the activity values in the fossil and a similar sample from the live animal. We take the formula that connects the half-life and the decay constant. We plug in the half-life value of carbon-14. Now we take the decay rate formula and plug in the values. Pay attention. We can consider that the initial activity is 100% and the current activity of the fossil is 25% of the initial activity. The half-life of carbon-14 can be taken from the previous example. Now we continue as in the previous example. Below, I leave you with some physics exercises from IGCSE Cambridge. They are simple, but they make the theory clearer.